Hey everyone, welcome to the next video. In this video, we're going to be talking about waves. Now, this is a fairly complicated thing to be studying with so little time left in the semester. If I'm being 100% honest, like I still struggle a little bit with these concepts. And so I am aware that this stuff is probably going to be a little tricky for a lot of people, So all I'm saying is just do your best. I don't really expect you to be, uh, you know, anything more than competent with the basics here. So just keep that in mind. And of course, I'm available to help as much as you might need me to. So anyway, with that out of the way, let's get started here. The first thing probably want to do is define a wave, right? Or rather define waves, let's say. So I'm going to say this. I'm going to say defining a wave can be a little bit tricky, but this is what we'll go with. And let's say that a wave is a disturbance of a continuous medium that propagates with fixed shape at constant speed. Now, like an example of this, for instance, that's almost so obvious. I feel a little silly saying it. Would just be like waves at the beach, right? And I would say like try to keep an image of that in your mind as we work through this stuff. And so there are different sort of ways to categorize waves, right? And the first distinction I want to make is between a traveling wave and a standing wave. And I think the best way to do this is just to show you a little video demonstration here. So let me bring this up really quickly, and I'll talk about this as we go through it. Okay, so I think this is pretty good. It's simple. I didn't have to watch any ridiculous ads to get this started, so hey, that's something too, right? So in this animation, right, on top there's a traveling wave, and on bottom there's a standing wave. So let's just get this going and kind of see. I might actually slow this down a little bit because it's a pretty short video. Let's play it at like 75% speed, maybe. Okay. So we see that the traveling wave, essentially the big difference here is that it propagates, right? That it's moving. This standing wave is kind of just like each point on it is just moving up and down, right? Whereas each point on this wave is moving up and down as well as moving to the right. And so hopefully, I'll run this one more time while we're talking. Hopefully this helps you kind of see the difference between traveling waves and standing waves, right? I think that if you can just keep this picture in your, or this I say picture, this, let's call it a GIF. If you can keep this GIF in your mind, then you're going to be okay as far as purposes of this class are concerned. Okay, so we said that there are traveling waves and standing waves, right? And I think that the existence of standing waves, right, also presupposes the existence of sitting waves. So here, standing wave, sitting wave, right? It's in a chair, right? Anyway, let's move on here. Okay, so then we also want to differentiate between. Actually, let's hold off on that. I'm going to show you another animation here, but let's just say then, focusing on traveling waves, right? We're going to say for traveling wave with time and position dependence. Let's say propagating, right? Propagating just means, moving, right? In the z direction. The corresponding function, right? The function that we use to represent this object must depend on the quantity z plus or minus vt, right? And I should say here propagating at speed v. And so it has to, well, we could put this mathematically, right? We could say that any function that we use to represent these things mathematically should look like this. We're saying just some arbitrary function of z and t, but it actually has to be a function of z plus or minus vt, right? And I just switched from f to g to, I don't know, just... G is just another function, right? F is one function, G is another function. Just arbitrary functions here. We haven't said anything really definite yet. Okay, and we'll see why this is after we derive the wave equation. But I just want to make sure that everybody's clear on this. So for instance, like you could guess, or let's do this. Let's say, for instance, I have some function, right? For instance, let's say we have a function, and let's call it, I don't know, like h of z and t, right? And let's say that it is, I don't know, like z squared times vt cubed. Well, this couldn't be a wave, right? Because it depends on the product of z squared and vt quantity cubed, and it doesn't fit this form, right, where we're saying that it has to depend on z plus or minus vt. And so we'll see later how we could directly show that this can't be a wave, but I'm just trying to give you a very quick example to show you that like this we could just categorically say is not a wave because it doesn't have this property of depending on the quantity z plus or minus vt. Now, the other thing I should say actually is that we are working essentially in 3 dimensions now, and there's kind of no way around this with waves. So I'm going to just, for instance, I'm going to plot in Mathematica here. It's just like a very basic, let me bring my screen over here. Like the most basic wave we could probably think of, right? And let's say that it's like cosine of z minus t. And this will depend on z. And let's just, I don't know, make up some numbers here. Z varies from -5 to 5. And let's also say t varies from -5 to 5, right? So this could be a wave, right? Like in this case, it would just be like my velocity is 1, or my speed is 1. So I'm fulfilling the condition that we just discussed when I plot this in Mathematica and assert that it's going to be a wave. So I'm going to get rid of this because it doesn't really need to be there, but let's see what this looks like. Right, so this is a 3-dimensional thing, and it looks a little scary. But if you can just like tell yourself or convince yourself like, hey, if I just look at this from the side, right, it kind of maybe obscures the time dependence, and now it just sort of looks like a regular cosine to me. That's fine. So as long as you can kind of always see, we're not going to be working like, how do I say this, like directly with the 3D nature of these things. Like we won't be, plotting them, trying to plot them in 3 dimensions. We won't be really doing anything like that. We just need to remember that we can look at the projection of a function like this, and it then becomes something similar to what we're probably more comfortable with, okay? So yes, we are essentially doing, we're essentially doing multivariable calculus here, right? But it isn't going to be so bad, okay? All right, so let's look at an example that is going to allow us to, actually, before we do that, I did want to show you one more video. I wanted to show you a video that shows you the difference between transverse and longitudinal waves, actually, because it's also important, I think, to distinguish between these 2 types of waves. Now, let's watch this. And this video is going to show us an animation of a longitudinal wave and an animation of a transverse wave. And we'll talk about what this means. Let me loop this, actually, and then maybe even I'll just loop it. That's fine. So the first example they're going to show is a longitudinal wave. And what we see here is that there's no vertical or transverse displacement from the equilibrium for the longitudinal wave. For the transverse wave, however, there is a vertical displacement from the equilibrium, right? If we think of the equilibrium as being, say, maybe this horizontal line here. And that's all there is to longitudinal and transverse waves, right? The longitudinal wave is going to have displacement from equilibrium along the direction of propagation, whereas the transverse wave is going to have displacement from equilibrium perpendicular to the direction of propagation, right? So here, displacement from equilibrium is in the vertical direction, and the direction of propagation was to the right. Here, the displacement from equilibrium is along this horizontal line here, but so is the propagation, okay? So hopefully this animation makes it clear what the differences are between these two kinds of waves. We will, I want to say, be focusing almost exclusively on transverse waves, though, for the remainder of this class. Okay, cool. Okay, with that out of the way, then what I do want to do now is derive the wave equation for you. So I'm actually going to highlight this just because this is important, and I want to make sure everybody realizes that it's important. So here, what we're going to do is we're going to imagine a very long string under tension T, okay? And let me put a quick diagram in here so you can see sort of exactly what I'm talking about. So what we're saying is, like, there's some string, maybe it's being wiggled or something, right? Like, you know, you could imagine that you have some dental floss and you're holding one end in your left hand and one end in your right hand, and you're just moving your hands up and down, maybe, say. That's kind of what the full picture here would look like, but we're zooming in on a very small bit, right, of the string. And so on our horizontal axis here, we have z, right? And this point we're just going to call z. This point we're going to call z plus delta z. And we want to write out the net force in the transverse direction, right? So vertical direction in this case, and see what that looks like. So let's do that. So I'm going to say, considering the let's say transverse net force on this little bit of string, we have, and so this is just going to be a difference of forces, right? We're going to have, so I'm going to write delta F here. We're going to say on the right, okay, if we identify the positive direction to be pointing up, positive transverse direction, then we have T sine theta prime, right? And then on the left, we're going to have minus T sine theta, right? So I don't think that there's anything, hopefully, too shocking about this. It is weird because we are, you know, again, this is sort of a three-dimensional thing, but you can't really see that in this diagram here, and that isn't going to end up presenting any issues at all. So hopefully that convinces you of what I was saying before. Okay, so I'm going to do a little bit of a tangent here. Wow, that was a pun I didn't intend, but it actually worked out kind of well. So what I'm going to say is, if these angles are small, right, and they are by hypothesis, then we can say that sine of theta is approximately equal to tangent of theta, okay? Like I said, I didn't intend that pun, but it just kind of worked out. Everything came together nicely. So to convince you of this, well, I'm just going to simply plot these in Mathematica for you on top of each other, right? So we can see that this is actually a pretty valid approximation to make. So what I want to do is I'm going to say show, okay, so I'm going to have Mathematica show me two plots. The first one is going to be sine of x, let me do theta, sine of theta, and we're going to say that theta is between negative 0.3 and positive 0.3. Now, these are in radians, right? Because Mathematica by default interprets angles to be radians. Okay, so if you want to see what, or if you want to figure out what this range of values would be in degrees, you could just go ahead and convert. But it's not super important for our purposes right now. And then I'm going to plot tangent of theta over the same range of values, right? And I think that's good. Let's see what it spits out here. And notice that, like, one of these lines is sine and the other is tangent, right? And I can't even honestly tell you which is which. I could, change the color or something, and then it would become clear, I think. But I'm not going to do, excuse me, I'm not going to do that, because the point is that we can make this small angle approximation here, and it's going to work pretty well for us, right? Because these two, I guess I shouldn't call them lines. They're curves, but they're almost indistinguishable except for towards the beginning and the end of the interval here, right? And so hopefully that convinces you that that this is a legal thing to do, that it's okay. And so anyway, with that being said, we can now write that, well, we can write that wherever we see a sine of theta or sine of theta prime, we can write tangent of theta and tangent of theta prime, okay? So I'm going to say this means that we can write, now do this. Okay, so we would then have t tangent theta prime, right, minus t tangent theta. And then we can write this, we could just factor out the tension, right, and then we have tangent theta prime minus tangent of theta. Okay, cool. All right, and so then let me put this into the document here, but I'm going to say if we identify tangent here with slope, right? And remember, if you think back to, say, like the unit circle or something, or even just like an arbitrary right triangle, tangent is opposite over adjacent, right? So we could kind of think of tangent as like rise over run. If we are considering the correct angle in the right triangle. But also think, back to the unit circle, tangent of theta is defined to be y over x, and that's also like slope, which we usually think of as delta y over delta x. Here, however, it's going to be delta f over delta z, but the idea is the same. And so what I want to say then is this, then, and this is where the math is I don't know, it's going to get a little weird maybe, but you're not going to have to like derive this yourself from scratch. You just kind of have to be able to follow along with what I'm saying, okay? So don't freak out if this is looking very strange to you. So I'm going to, instead of thinking about slope now, I'm going to think about derivatives, right? Because very loosely speaking, we can identify a derivative with slope for a given function, okay? And so all I'm saying is that, remember, this is a partial derivative, right? And we could really have just written, the regular d's here, and I don't think anyone would have been too terribly upset, but I'm trying to be a little bit, I guess, rigorous. So I'm going to write it as a partial, but remember that this is just the derivative of the function with respect to z. And we're going to evaluate it, right? That's what the subscript means. We're going to evaluate it at z plus delta z, and then we're going to subtract from that it evaluated at z, z, at z. Okay. Now, if, right, if we divide this by delta z, okay, let me say this. And I want to get this into a particular form. This is why I'm doing this, so it looks like essentially a second derivative, right? That's the point here. What we have then is we have something like this. Let me just copy and paste this. And then I'm going to just divide this by delta z. I should divide both sides though, actually, if I want to be careful. So delta z, and then we can divide this side too, just because it should be divided by delta z. Well, here, right, let me write this one more time. I'm going to just factor out a t, essentially. This term, right, if you think back to Calc 1, actually resembles the limit definition of a derivative. And since we don't have the function itself up here in the numerator, we have the first derivative, then this is actually just the second derivative of, well, I shouldn't say, so let me say this then, okay. In the limit as delta z approaches 0, this becomes the second derivative. Wow, spelling is hard. Derivative of f with respect to z. And again, it's okay if this is something you haven't seen in a while or thought about in a while. It's totally fine. But I just want to show you how this kind of looks. So then we could write this as let's see. We could write this as like maybe this. Say that this expression goes to t times the second derivative of f with respect to z. Okay? And so then, let's think about what we have here, right? Well, this allows us to write then that this, right, now just multiplying both sides by delta z, this expression that we found, right, for the net transverse force works out to be t times the second derivative of f with respect to z times delta z, right? Okay. Now, remember that when we started, this was, right, so this is what we started with, and we were saying, well, this is essentially the net force in the transverse direction, right? Along the direction of f here. Now, let's think about Newton's second law, right? So we say applying Newton's second law in the transverse direction, we have, and remember we started with delta f, right? And we're going to say that, actually, I need to do one more thing here first before we apply Newton's second law. So what we want to do is we want to write the mass in terms of the mass density. And this, it probably won't be clear why I'm doing this now, but later it will become very clear why I'm doing this. So let's just do a little sidebar here and say, if the string has linear mass density, mu, and remember that this is defined to be, I think I used a different symbol last time we talked about this, but I'm going to call it mu now because I think that's the sort of canonical choice here. Remember, the linear mass density is just the total mass over the length, right? And so the mass of this little bit of string that we're considering is this. We can write that m, just essentially rearranging this and changing the L to delta z, and I'll talk about that in a second, but we can just write that this is mu delta z. Okay, and remember that our length is delta z, right? Because we're thinking about going from z to z plus delta z. So this is our L, essentially. And the reason that we can use linear, even though this doesn't really look like it's, you know, a horizontal line, for instance, is that because this is an exaggerated picture, right? And these angles are small. So this would probably look a lot more horizontal if it wasn't so zoomed in, okay? Anyway, so that's what we have. Now we can apply Newton's second law, right? Because we can write that the mass, that this net force in the transverse direction can simply be expressed as the mass times, and I'll just say the transverse acceleration, I suppose, but it doesn't really matter. We're not going to continue to call it this. And we can rewrite this as, well, remember we just said that the mass was mu delta z, and we can think back to writing accelerations in terms of time derivatives and simply write that the acceleration in the transverse direction is just the second derivative of f with respect to t, right? Now, you might be wondering, like, why the hell are we doing all this? And that's a great question to ask. And there is a point. We are going to get somewhere, I promise, so just bear with me. So let's see then what we have. We're going to take this. Let me just say then, this gives. And remember that this was our delta f, essentially. And this was just the other side of Newton's second law, right, the MA side. And so this is what we have. Now we can cancel delta z because it's common to both sides, right? And let's actually, I don't know, let's do this all at once. So what I'm going to do is I'm going to cancel delta z, and then I'm going to divide both sides by the tension. So what we end up finding is, I'm going to check to make sure this is correct. Yeah, I think it looks good. Okay, what we end up finding is that the second derivative of f with respect to z equals mu over t times the second derivative of f with respect to t. Right, so the second derivative of this function with respect to z equals mu over big T times the second derivative of this function with respect to t. And this is the wave equation. I'm actually going to highlight this because, as I said, it won't be really important for the remainder. This particular form of the wave equation, at least, won't be particularly important for the remainder of this video, but it will be later when we talk about like sound and frequency, right? So I am gonna highlight this. This is a good result to remember. But let's look. So we're done with calculus for the insane, right? We're gonna now we can just do some good old-fashioned dimensional analysis. So let's check the dimensions of this mu over t term, right? So you all know the drill by now, right? And just write the square brackets to indicate we're looking at the dimensions. Well, we already said, right, that the linear mass density is just a mass over a length, so it of course has dimensions of mass over length. Now, I'm going to be very careful about this. Actually, I want to write this as an F, because tension is a force, right? And so if we're thinking about the dimensions, and that's all we care about, we can just write that we're multiplying this by 1 over, well, that we're multiplying this by the dimensions of 1 over a force, because tension is a force. So let's write this out maybe a few more times here. Now, the dimensions of force are going to be mass times length over time squared. So the dimensions of 1 over force are going to be time squared over mass times length, right? And the way that you could, if this isn't clear, the way that you could remind yourself of this is just remember that a force is most generally given by a mass times an acceleration, and you can, check the dimensions of a force that way, right? And anyway, we find, right, that this, once we cancel the m's, that this works out to be a time squared over a length squared. But hey, this actually seems like it might be physically meaningful because these are just the dimensions of 1 over a speed or velocity squared, right? We'll say speed squared. So that means we can identify this term here right, with 1 over v squared, where v is the speed at which the wave is propagating. So let me say thus, and this is going to be very important. This is probably like the most important result from this video here. And that we find the second derivative of f with respect to z is just 1 over v squared, where v, again, is the propagation speed of the wave, times the second derivative of f with respect to t. And this is the general, we'll say that's the one-dimensional wave equation, right? Because you could have a wave equation where you have like x's, y's, and z's, and that would be the three-dimensional wave equation, which we won't concern ourselves with. This is good enough for our purposes here. So this is the wave equation, and it's very important, right? This pops up a lot in physics and in some surprisingly different contexts. And I think the two most common, though, would be for like sound waves and then also electromagnetic waves. Now, we won't talk about electromagnetic waves at all here, but you should know that a very similar, well, that this equation in essence governs electromagnetic waves, and obviously sound waves. Okay, so let's look at an example then, and I'm going to lean heavily on Mathematica for this because I can't really be trusted to take second derivatives and all that. So I'm gonna do this for you, though I'm going to show you what I'm doing here. But what we want to do here for this example is just consider these two different functions and show that this first one here satisfies the wave equation and show that this second one does not, right? So how might I do this in Mathematica? For those of you who use Mathematica, this would actually be, well, I think this should be useful because, you know, you'll have a good amount of math and derivative taking to do on the next assignment, the final optional assignment, but remember, you should all do it. So what I'm going to do is I'm just going to define a function here. Let's say a function of f of z and t. And so the way that I do this in Mathematica is I write f, then I do square brackets, and what I'm telling Mathematica by writing this is that, hey, this function I'm about to give you depends on z and t, okay? And then I have to do the colon equals to really convince Mathematica that this is a function. And so I can write that, I can just put the function in now. So let me make sure I get this correct here. And so there we go. I've told Mathematica this is my function. Now I can say, hey, Mathematica, tell me what the first derivative of f of z. Actually, we can do one better. We can just have it take the second derivative, right? And the way we would do this is just by saying first derivative would look like this, right? Second derivative, simply use curly braces and then just put a comma and a 2 in there. And now it's going to give me the second derivative of this function with respect to z. And this is what it ends up being, right? Okay, cool. Now I can check the other side of the wave equation, and I can just say, hey, Mathematica, now give me 1 over v squared times the derivative of this function, or the second derivative of this function with respect to time. And so we find that this works, right? Because this is the left-hand side of the wave equation. This is the second derivative of this function with respect to z. And then this is 1 over v squared times the second derivative of f with respect to t. And these are equal. So we've shown it, right? Let me just say, I guess, Mathematica, right? Okay, cool. So there's that. Now let's look at this other function, and I'll just define this. I'm gonna use a script f to define this one, but this will also depend on z and t. And this one actually wouldn't be so bad, I think, to take the derivatives by hand, because exponentials are nice, but let's just do it this way. So now I'm saying, okay, Mathematica, this is my other function. I'm defining it with the exact same syntax. I'm just using a script f instead of a regular f. So there we go. Now let me say, okay, well, what's the derivative of this function that depends on z and t, or the second derivative of this function with respect to z? So we find this, right? Now let's try the other side of the wave equation. We're going to say 1 over v squared. Let me do this. And then times the derivative of the second function of z and t with respect to t, and then do it twice for the second derivative. So that, and I mean these are not going to be equal, right? I mean we could expand this so it maybe is a little clearer, but there's no way that these two functions, or I should say that these two derivatives are going to be equal to each other, and that is including the factor of 1 over v squared in front of the time derivative, right? But the point is this doesn't equal this. So we see that this doesn't satisfy the wave equation here, right? And so you could check this directly. You know, I'll probably give you some of these to work out on your own for the final optional homework assignment. And you'll get a little bit of practice with that. Okay, cool. So then let's move on. There are just some things that we need to talk about as far as waves go. Like I would say they're the quantities of interest when it comes to talking about waves. So let's look at a snapshot of the wave from the previous example, right? So I'm going to say from example 20.1a. Because 20.1b we just showed is not a wave, right? So let me do this. So this is what it might look like, and we're going to look at it at time t equals 0, and this is kind of what I was talking about when I said let's look at the projection. So in the diagram here, there's not really anything to indicate that this has time dependence, but it obviously does, right? Because there is a t inside this cosine here. But anyway, this is what we have, right? We want to think about it at time t equals 0. So let's get some stuff out of the way. I'm going to say here, as with simple harmonic motion, delta is the phase constant. And again, this is just really a mathematical convenience that allows us to always describe these things with like a cosine function if we feel like we need to. Though you could use sine, and I don't think it really matters. But that's all it really does. I'm going to say we ordinarily choose, and this holds for simple harmonic motion too, actually, values of delta. Let me try to. Okay, cool. Such that delta is an element of this closed interval between 0 and 2 pi. Right, so delta can be 0, it can be 2 pi, it can be anything in between. And the reason for this convention is just because, you know, these trig functions, for instance, they're periodic, right? So there's any number of deltas you could actually choose that would make this a thing we could do, but we have a convention where we just choose delta to be between 0 and 2 pi. Now, I know that last time I was writing phi, and now I'm writing delta, and I said that I would try to not write phi, but I'm just going to write delta because my diagrams have delta in them, and I don't want to have there be any inconsistencies. But you can just write phi instead, and that's totally fine. There's no reason you can't do that. Also, if the z thing is bugging you, you can always write x too. It doesn't really matter, right? So, you know, I don't care if you want to write x's and phis instead of z's and deltas if that's what you're more comfortable with. Okay, cool. So let's talk about the wavelength, and we're going to say lambda is called the wavelength. And as you can see from the picture here, right, the picture is showing lambda to be the distance from a trough to a trough, right? These low points are called troughs, or I should say these minima are called troughs, and these maxima would be called peaks. And so lambda just tells us the distance from trough to trough, or equivalently from peak to peak, right? Now let's put this thing to work for us a little bit here. So I want to say, thinking way back to one-dimensional kinematics, right? So let's recall the generic definition of 1d velocity. And remember that we had this was v sub x is defined to be a change in x over a change in time, right? Now, if we write that delta x goes to lambda and delta t goes to the period, remember the period was just the time required for one complete cycle, then we have this. The propagation speed of the wave is given by lambda over big T, right? We can totally write this because remember this is a distance, or this does have, I should say, dimensions of distance, and this has dimensions of time, of course. And so, just to refresh your memory on something, remember that also the period can be written in terms of the linear frequency, and the period was just found to be 1 over the linear frequency in a previous video, right? So this then becomes v equals lambda f, and this is a very important equation, right? It relates the propagation speed of the wave and its wavelength and linear frequency, okay? So let me say this. So this is the propagation speed of the wave. Now you might be wondering, right, since we're talking about speeds and such, how to determine the direction in which a wave is propagating. Now, I don't know if you have a better way of doing this, and if you do, I'd be curious to hear it. But for me, like, I cannot look at something like this and be like, oh yeah, this is going in the positive z direction or the negative z direction, right? And that's fine. I mean, because I know how to show the direction in which it's propagating if I need to, and I'm going to just tell you how you would do this. And I probably will have you do this on the homework assignment. So I'm going to say, I mean, so we know, right, because, let me just come back to this, because we have it in the sketch here, we know that this is going in the positive z direction, but say that wasn't on the sketch and you didn't know, right? How would you determine the direction of propagation? So I'm going to give you a little blueprint for how to do that. Because sometimes it can be a little ambiguous when looking at a diagram showing a static representation of a wave. So I'm going to say one way we could do this is like this. Okay, so we write the equation, and I'm not going to do this as part of the video here because, like I said, I'm pretty sure I want to have you do this for the homework assignment, but I'm going to tell you how you do this. So we're going to write the equation for the wave at time t equals 0. Okay. So we just look at that equation, right? The a cosine blah blah blah. Just plug in a 0 everywhere we see t. Okay, not so bad. Then we write the equation for the wave at t equals the period, and remember that this can be written as 2 pi over omega, and as we'll see momentarily, this can also be written by or as 2 pi over kv. Don't worry about this right now because we'll talk more about k and what it means in a little bit. And then we just demand that f of z0, right, equal f. Now, as time goes by, z is going to change, right, by some amount delta z, let's call it. And then the later time that we're considering is just the period, right? And so we just equate these two expressions, and we solve for delta z. Okay, so it's not too bad. It's a little bit tedious, right? But it's something we can always do. I'm going to say, just to show you, but you're just because I say this in the video doesn't mean you have to. You can just say, oh, you know, you said it in the video for the homework assignment, right? I'm still going to want you to show this, okay? But I'm just going to say, so for instance, if delta z is greater than 0, the wave is propagating to the right. And we're thinking about the wave, the specific wave from the example. Because this obviously is going to depend on the how the signs, the SIGNs of whatever you have in front of Z and whatever you have in front of omega or kV or whatever are. So I'm going to say, for instance, if delta Z is greater than 0, the wave is propagating to the right. If, for our example, and if delta Z is less than 0, the wave is propagating to the left. So let me just finally say the wave f z of t equals a cosine k z, and I actually think I'm being kind of sloppy here. I don't think, have I talked about omega? I don't believe I have, actually. So let me just tell you that we'll see very soon that we can go, and I did, I think, hint at this, but we can write this in the form that I'm writing it now, right? So instead of writing this as the argument of cosine, we can also write kz minus omega t plus delta, and I'll show you how that works in a second here. But this, what I'll say is that this is the most common way to write the waves, and it's probably the convention that I'll stick with. Anyway, I'm going to say that this is propagating to the right, just for an example. Now, if you had the same expression, but there was a negative sign in front of k, then that wave would be propagating to the left, okay? So let's talk about some things, because I should tell you what k is, and we should also see how we can go from v to omega and vice versa. So let's say k, right, this is called the wave number. And this, I think that like this is one of the trickier things to have an intuition about for this stuff. So as long as you can remember the definition I'm about to give you, should be fine. But I'm going to say when z advances from, say, 0 to 2 pi over the wave number, the cosine completes one full cycle. And so from this, right, we can say that the wave number is defined to be, and we're going to write that k is defined to be 2 pi over lambda. Okay, and again, like I said, the intuition, it can be a little bit tricky here, but if you can just remember that it's defined to be 2 pi over the wavelength, that's going to be perfectly fine for our purposes. And let me put this in yellow too, because this is pretty important. Okay, cool. And then now we can come back to the picture here, and we can look at this delta over k thing, and we can see that this kind of just tells us how the wave is delayed. Because normally for a cosine, the central maximum would occur right here at t equals 0 and z equals 0, right? But we see that for this wave, for instance, it doesn't. It's delayed a little bit. So let me say that furthermore, the quantity delta over k tells us, I don't want to say the distance. I'll just say this. I'll just say how the wave is delayed. I.e. the distance of its central maximum from the origin. Let's just say it like that. Because this would occur at z equals 0 for a pure cosine, right, where there's no phase constant in there. Okay. So the last thing I'm going to say then is that, well, it's not the last thing, but the last thing in terms of this little section where we're just defining things that are going to be useful is that finally recall that, and remember in the video on simple harmonic motion, we went and we said that we can write the angular frequency in terms of the linear frequency like this. We just multiply the linear frequency by 2 pi, and that gives us the angular frequency. Now, we'll keep the 2 pi as it is, of course. We couldn't really substitute anything for that even if we wanted to, but remember that the frequency is just 1 over the period, right? And from the wavelength equation, we see, right, that 1 over t is v over lambda, because I can always just take this equation that we have here, right, put a 1 there, and then divide this by lambda. And so I'm going to take the equation that we were working on just now and substitute in v over lambda for the reciprocal of the period. So this is, now we said that this is 2 pi times v over lambda, okay. And then we need to make one more substitution. We can write 2 pi v over, and then from our definition of k, right, this tells us that lambda, I'll write this too. This tells us that lambda is equal to 2 pi over k, right? And so here we can write that lambda is 2 pi over k. And then upon canceling the 2 pi's and simplifying, we find that omega is just kv. And that's what allowed me to write the equation here in terms of omega, right, instead of in terms of v, like that. So same equation. And this is also a pretty important relation to remember, so I'm going to highlight this one too. Cool. And let me just show you how this is, what this looks like, just step by step, I guess, because I should say. So we see that omega equals kv, and anywhere we see v in our equation for a given wave, we can write omega over k instead. For example, thinking back to the wave from the example we had, we called it f1, right? So f1, this was a cosine k z minus vt plus delta, right? And then we can expand this out. We can say a cosine kz minus kvt plus delta. And then finally we can write a cosine, let's see, kz minus omega t plus delta. Okay, cool. So there is the justification for writing the wave as I did in terms of omega instead of v. Okay, let's look at one example and then we'll be done for this video. So this is just going to give us a little bit of practice with writing out the equation for a wave if we know some things about it, right? Like if we know its amplitude, its wavelength, its speed of propagation, and we know what it is evaluated to at t equals 0 and z equals 0. Though we could do this for some other, non-zero time and non-zero position, but I wanted to keep this fairly simple. So we start with the general form, right, which we're going to now write as f z of t, z and t equals a cosine kz minus omega t plus delta, right? So we know that omega equals kv, and so v no, I don't think we actually want to substitute this way. I don't think I need to do this actually. So let me just say that we can write this then. I was going to do some algebra, but I don't think it's actually necessary. So if omega is kv, we can just write this then as a cosine kz, right? And now where we see omega, we just put kv minus kvt plus delta. Cool. Okay, so we're getting somewhere. Now we have, you know, made a substitution. And then let's also remind ourselves that we also know that k equals 2 pi over lambda. So we're simply going to eliminate all the k's for 2 pi's over lambdas. So then we have f z of t equals a cosine, and then now we write 2 pi over lambda z minus, and I'll copy and paste this because it's just going to be the same prefactor here, 2 pi over lambda vt. Delta doesn't change, can't really do anything with it just yet. And so now our equation looks like this. So all that's left to do is to evaluate this at time t equals 0 and position z equals 0. So let me say finally we have, and I'll write f of 0, 0. And now this is really going to, you know, tidy or get rid of a lot of things for us because, well, this term just goes to 0, right? Because z is 0, so that's 0. This term is also going to 0 because this involves t, and t is 0 here, right? So 0 minus 0, and then delta we just leave unchanged because what we actually want to do in this step is solve for delta. Now, what did we say? We said that this equals 0.05 meters, right? But notice that the way that I wrote this, that this is just a divided by 2 symbolically, right? So you want to keep an eye out for things like this. Though I'm sure that if you were just even going through with the numbers and not really paying attention, it would still probably pop out. But the point is just that the amplitude of the wave at time t equals 0 and at position z equals 0 is just half the full amplitude, right? So we can write this. We can write that this is a over 2. And then we see, right, that a cosine delta equals a over 2. And so then cosine delta is just 1/2 if we cancel the a's, which we can and should, right? Because there's an a on each side of that equation. And then we finally see, right, that delta equals pi over 3. This is a nice angle, but if you had a nastier one, you could just do arc cosine of both sides here, right? Figure out what it is numerically. And so our equation then finally becomes, all we really have to do, and we don't have to even do this, but I'm going to do it. And I would just suggest that you do too when you have like a nice value for delta. If it's just some gross decimal approximation, then don't bother. But I'm going to say that this gives, and we can write our function like this. And there you go. Now we've written the wave, so it only depends on things that we were given in the problem statement, right? We were given lambda, we were given v, and we solved for the phase constant. Okay, cool. So that's it for this video. Quite frankly, these headphones are kind of making my head hurt. They are isolation headphones, which is nice, but like they're really squeezing on my skull. So let's end here. There will be one more video on waves, and we will specifically be talking about sound, and that'll be it. All right, I will see you in the next video.